Hello, I'm Charles Kulick. Today I'm presenting a tidbit of mathematics in recursive sequences in hailstone problems. This research was performed by Alvaro Carbonero, Beth Ann Castellano, Carrie Smits, and myself at the Lafayette College RU in 2019. With the help of our amazing advisors Dr. Gary Gordon and Dr. Brittany Shelton, and the monetary support of the NSF Grant 1560222. Now let's take a look at the problem. The original problem definition appeared in the Math Horizons magazine in February 2019. We define a function piecewise for all positive integers. Any odd integer, we simply add 1. Any even integer, we simply divide by 2. This function has a number of interesting properties that we care about. Let's take a look at these through some examples. First, f of 7. 7's odd, so we simply add 1, 8, simple enough. But what if we take f of 8? Divide by 2, we get 4. f of 4, divide by 2, we get 2. f of 2, 2 divided by 2, 1. Interesting. Let's stop at 1 for now. f of 5, we get 6, 6, 3, 3, 4, 4, 2, 2, 1. You might notice that both times we eventually got to 1. Does this happen for any positive integer? Well, it turns out, actually, yes. We can show that all positive integers go to 1. This isn't a terribly interesting proof, but it is important that we know this to be true. We care more specifically about how many steps this process takes. For example, in a rigorous definition, let's let an be the number of successive applications of f needed for n to reach 1. So in our examples, we see that a7 is 4, as there are the 4 listed steps to bring 7 to 1, and a5 is 5, as the 5 listed steps. So not terribly complicated. However, we need more than just a notation to get one number and its number of steps. We care about the set of numbers with that number of steps. And to that end, we define Bn as the set of all integers m such that a sub m equals n. So this is a set containing all integers that take exactly n steps to reach 1. I will note that at 1 the process terminates, so we're ensuring that everything is unique, because we can go 1, 2, 1, 2 forever, but that's not very interesting, obviously. As an example, b of 1 is 2. It's the only thing that takes 1 step to get to 1. And the cardinality of b1 is 1, just to introduce some notation that we're using in this talk. b of 5, we have 5 elements listed here. We can verify this pretty easily. It's still a very low n. And b of 5 has a cardinality of 5. The very interesting thing that we found and that the original problem focused on was this recurrence in the cardinality. If we take n greater than 2, we can actually prove that the cardinality of Bn equals the cardinality of Bn minus 1 plus the cardinality of Bn minus 2. Let's walk through this proof together. These ideas are vitally important for what we eventually show. So for each element in this big set Bn, if it's even, then we know that it's going to be divided by 2 and it will be in Bn minus 1. If it's odd, then it's going to be added with 1 and then divided by 2. And then that makes that expression exist in Bn minus 2. Let's take an arbitrary element in Bn minus 1. Then 2 times that is in Bn. And an arbitrary element in Bn minus 2, 2 times that minus 1 is in Bn. This shows that everything in Bn is in one of these lower sets, and only those things in those lower sets are in Bn, showing that the cardinalities have this nice addition property. What's even more interesting, perhaps, is exactly how this plays out in our specific case, because B1 is a singleton set of 2 and B2 is a singleton set of 4. So our initial conditions are a 2-term recurrence relation with 1 and 1. The Fibonacci sequence. There we have it, a connection to perhaps the world's most famous sequence. However, we are interested in modifying this problem into a very general sense. Now, this isn't as general as it could be, but we're going to carefully modify this function as we see here so that we still get this convergence behavior to 1. We need everything to converge to 1 to really ask this sort of question in a sensical way. Let's let c be a positive integer and k be a natural, and define gn as this function c to the k times n minus 1 if it's not 0 mod c, or n divided by c if it is 0 mod c. Okay, we can show that all of these sequences reach 1. Again, it's not a terribly hard proof. It's the same thing that you would do with 2, just it's not terribly interesting to show. Let's update our definitions. This is just a bit of notational bookkeeping. AN is now the number of successive applications of G it takes for n to reach 1, and BN is defined likewise. Our main result is that for any function, given any two parameters, c and k, we have a recurrence relation that we can make, so long as your n is large enough to be valid. Namely, that you have the cardinality of Bn equal to the sum as I goes from 1 to c of the cardinalities of Bn minus 1 minus this quantity, c minus I times k plus 1. This is a really, really nice formula. We see that, obviously, because we've seen it, the Fibonacci is a subcase of this. What else is hiding here? For any two parameters, we can get a recurrence relation with c terms. It's a very nice way that we can go from any one of these hailstone problems to a sequence, and from many recursive sequences to hailstone problems. To take a look at this result in a few specific cases, just to see some of its more exciting and easier to state properties, we're going to let c equals 2. Then our function we're considering is the one that we've started dividing by 2, but also we're multiplying by a power of 2 now in the odd operation, as it were. Then if k equals 0, we have the Fibonacci. We already solved that. K equals 1, we have n minus 1 and n minus 3 appearing. K equals 2, n minus 1 and n minus 4. And as you might have guessed, given a k, we can show that it's just n minus 1 plus n minus k plus 2. So we get these nice two-term recurrence relations every time that a 2 shows up. Not bad. Let's let k equal a small value and see if we get anything that's equally as nice. For k equals 0, it's just n plus 1 and n divided by c. So, again, for 2, we've seen it, not interesting, although it's the incredibly interesting Fibonacci sequence. C equals 3, we have a 3-term recurrence, n minus 1, 2, and 3. C equals 4, a 4-term recurrence. And again, as you might have guessed, the cardinality of Bn is simply all of these sequences n minus 1 up to and including n minus c. C terms there. This would be negligent to go without mentioning its closeness to a famous mathematical problem. You might have seen this before, where the name hailstone sequence comes from originally. If we let hn be a function 3n plus 1 if odd, or n divided by 2 if even, does every number reach 1 after repeated application? And the answer is, no one knows. No one knows. This is called the Kulick conjecture, famous unsolved problem. Generates lots of mathematical attention, including minds as brilliant as that of Terence Tao. This is famously open and famously difficult. Note that this is one of the big reasons why we stepped around multiplying the quantity n plus 1 by a number in our generalization, and not having an plus b, because that opens up the door to these weird convergence type questions that even the wider field of mathematics is not quite ready to deal with yet. And we'd like to conclude this talk with some thank yous. To our advisors, Dr. Gary Gordon and Dr. Brittany Shelton, to the NSF for the support, and to Lafayette College. And of course to you. I hope you enjoyed this little bit of mathematics. Definitely look into the Kulick conjecture if this is interesting to you. There is more than enough mathematics being done on that to keep you entertained for days on end. And stay safe, everyone, in these trying times. Thank you for watching.